Now in Chapter 2 we're going to talk about functions and models. So if you liked Algebra 2X content, this chapter is right up your alley. The first section covers 4 objectives, and it's these first 4 right here. 3 of them you're going to be very familiar with. That's going to be 2, 3, and 4. Number 4, determine if a relation or a graph is a function using a vertical line test or mapping. 3, evaluate functions given a binomial expression. And 2, evaluate functions given a numerical input. And then the fourth one, or in this case number 1, that is going to be new for you, is just vocabulary about identifying independent and dependent variables in a scenario. So let's go ahead and do that. The first thing we need to do is talk about some vocabulary about a function. And that's about a relation. A relation is just a set of ordered pairs, such as this. And this set of ordered pairs is actually missing these brackets here. These brackets actually identify they're a set. It just means it's a group of ordered pairs. Recall from ordered pair structure that the first value is typically our x and the second is y when we're on the coordinate plane. Also, what we would say in terms of function notation, the x value is typically what we call the input. We normally choose what x is. We then put it into an equation, and from there we end up getting what the output is, or the answer, which is the y value. Now it's going to lead us to these 2 new vocab words. The first one is the independent variable. In this ordered pair, one of these is considered the independent variable. It's the one that we get to choose, and that is going to be the x variable or the input variable. And this is normally the first variable in the relation. So in this case, that would be our x. The dependent variable means this variable depends on the other, and that is going to be the second variable in the relation. And it typically is called the y, or the output. And the dependent variable is right there. Now, let's talk about the definition of a function. A function by definition is a set of ordered pairs x and y, like we have above, in which each first component x is paired exactly with one second component y. So basically that means every x can only be matched with one following y answer. Now the definition of a domain we need to talk about. The domain is going to be basically all of our inputs, or the x values, or as we just learned above, we're going to call that the independent variable. Okay. Whereas the range, that is going to be all of our outputs. It's the y value, and we call that the dependent variable. Good way to remember this, by the way, ordered pairs are x and y alphabetically. The domain comes first, so that's the x. The range comes next, or second, alphabetically, so that ends up being the y value. Now let's take a numerical look at how you determine if a relation is a function. Now I want you to take a moment and take a look at these 2 different relations. We have the F relation and we have the G relation. I want you to pause the video and determine for me, are either one of these 2 or both of them considered to be functions? So pause the video, take a moment and determine, is F a function and is G a function? Hopefully after you've looked at that, you determine that the first relation is actually a function. Again, definition of a function, for every x value there's only one output. So every time I put in a 1, in this case I get a 2. When I put in a 2 I get a 4. When I put in a 3 I get a 6. G is not going to be a function, and it actually breaks right here with these 2 ordered pairs. In this case I put in a 1 and I got a 2. Not a problem. But the second time I put in a 1, this time I got a 7 back, which means this would not be considered a function. On here, they're going to ask you to list the domain and the range. And the one thing I do want to highlight is this. If I were to list the domain, what you want to do is keep 2 things in mind. You always list the values in numerical order or in increasing order, and you never list repeats. So the domain for this function, I would say, is 5, 6, 7, and 8. and I'm going to put that in set notation. The range in this function, be careful. The number 3 happens twice and the number 1 happens twice. You just list them one time, so I would say the range is the number 1 and the number 3. Now this slide is really just bringing us back to vocabulary and some mathematical shorthand. So let's talk about the corresponding definition of a function. This is just more of a real mathematical terminology. Again, function for every x is exactly only one y. But they may also say it this way. A function is a correspondence between two sets, A and B. In this case, we could talk about our x's in our ordered pairs and our y's in the ordered pairs, in which each element of A corresponds to exactly one element in B. Okay? So just be familiar with that also being a function definition. Another definition is, what is a real function? A real function is a function whose domain and range is the set of all real numbers. A very simplistic definition. So what you first really want to remember are, what are the real numbers? And real numbers are right here in shorthand. Real numbers, by definition, folks, you can graph them on a number line. So can graph on a number line. Good to keep that in mind. Pretty much any number can be graphed on a number line except an imaginary number. So for example, you could graph the number 1, a negative number. You could graph a fraction. You could graph a square root, and anything of that nature. You could also graph the number pi. You can't graph an imaginary number, which is a square root of a negative, so just know that. Another word for definition we want to talk about is the member or element. If x is said to be in set A, we say that it's a member of set A or an element of set A. So let me do this for example. If I say let x be the number 3, the number 3 is a real number. It can be graphed on the number line. So I want to do mathematical shorthand and tell you that x is in the set of real numbers. So what I would do is I would say x is an element of, and that's just a little epsilon or the e, real numbers. This is mathematical shorthand, which is great. You do not have to do that. You could actually just write a sentence that says x is an element of real numbers, or you could do this. And in this mathematical shorthand, the shorthand for real numbers is a capital R with this line through here. And again, this symbol here is the element sign, is how you would write it. The last thing on this slide I want to talk about are these other three symbols. We have integers, rational numbers, and natural numbers. And what you want to be able to distinguish is, which one is the larger group? Are there more real numbers? Are there more integers, more rational, and more natural numbers? So I'm going to go on to another slide and just show you the relationship between these three, or really these four. And then you're going to also notice they all have their own shorthand. Let me just clarify the shorthand for integers. Integers, by the way, are positive and negative whole numbers. So let's jot that down. Positive and negative whole numbers, including the number 0. Okay. Real numbers are anything that can be on a number line we talked about. Rational numbers are any numbers that can be written as a fraction. That's what I would write down. And the last one is natural numbers. Natural numbers are basically just positive whole numbers and the number 0 again. So it's a subset of the integers. Shorthand for those, the natural number, it is a capital N, and with its kind of slash there. Rational numbers is just the Q, and integers is a Z with its little slash right there. And let me show you how they're related on the next slide. So here's a quick sketch of how the numbers are kind of embedded in each other. The natural numbers, again, I said, are the whole numbers and 0, or the positive whole numbers, so we have 0, 1, 2, 3, and so forth. And then integers are an expansion of that. The integers are the natural numbers, so we have 0, 1, 2, 3, and so forth, but we also have the negative whole natural numbers, so we're going to have negative 2, negative 1, and so forth on that. So those would be the integers. Now the rational numbers, it includes all natural numbers, all integers. In addition, though, it includes numbers that we can write as fractions. So it'll be all of these numbers here and these numbers here, but it would also be, for example, the number 2/3. the number 5 halves. But it can be written as a fraction. Does it include the number 0.2? Sure, because 2/10 is actually a fraction in itself. 2/10 is 2 over 10, which is actually the same as 1/5. So decimals can also be rational because decimals can be written as fractions themselves. And the last thing is the real numbers. The real numbers are comprised of natural numbers, integer numbers, rational numbers, so the fractions. In addition to, there's other numbers that we can't write as fractions, and that would be, for example, like the number pi. That's considered to be real. We consider the number square root of 2 as a real number, but not a rational. I can't write that as a fraction. The square root of 3 can't be also. So those would be all the real numbers or everything in this box. Okay, let's get to another objective. This objective talks about defining independent and dependent variables. Remember, independent is the input or the x, dependent is the output or the y. Here's our scenario. A bakery charges $2 per muffin. Customers get a $2 discount for every 6 muffins purchased. Which statement is true to say? Is cost is a function of the number m of muffins, or is the number m of muffins is a function of the cost? One of these two statements is the right relationship. And I'm going to tell you, for this case here, the correct answer is going to be the first statement. The cost is a function of the number of muffins. Okay, so the cost is determined by how many muffins we have. That in itself is telling me which one is the independent variable. So if I say which is independent, which one when you go to the store do you typically choose? Do you choose how many muffins you want to purchase, or do you choose how much money you want to spend in general? Okay. Typically you're going to go to the counter and you're going to tell the person how many muffins you want. That's your independent variable. So the independent variable is the number of muffins. Okay. Therefore, the cost is dependent, this should be with a T, on the number of muffins. So cost is your dependent variable. Now, we know that the independent variable is the input or the x. That means domain. The dependent is the output or the y. That's the range. Now, this is a real life example. So think about this. If the number of muffins above, we said actually could be symbolized by the letter m, what would you say is the domain of this particular example? When you go to the store, what are your possible options of how many muffins you're going to order? Okay. All right, you're probably going to order either 1 muffin, 2 muffins, 3 muffins. Assuming they're not going to let you order 3.5 muffins. You have to order a whole muffin. You possibly could order 0 muffins, by the way. Maybe you're just going to talk to someone and keep them company. So the domain of this function, we would say, is all the m's are either going to be greater than or equal to 0. But what's special about this case? The m's, this is shorthand, are all elements of integers that are positive. Now, for most of you, you do not need to know how to write this shorthand. This is more, if you want to know that shorthand, you can use it, okay? That's what this says. M is an element of all the positive integers. So 0, 1, 2, 3, 4, and so forth. Now, the range is the cost. The cost structure for here, again, it's $2 per muffin, and you can get a $2 discount for every 6 muffins you purchase. So you need to think about, will you ever need to have some change? Or are these just going to be bills that I'm using? Okay. The cost of these muffins is always either going to be $2, $4, $6, $8, or what have you. So the range for here, they said let C be cost, fine. We're going to say this cost is either going to be greater than or equal to 0, because I may buy no muffins, which means the cost is 0, or I may buy more. In this case, I'm going to say the cost is also an element of all of the positive integers, is just the shorthand. Now, descriptions of functions, some things we've already seen right now, that functions can be represented in terms of, we've seen them in ordered pairs. We've also seen them in terms of words or equations, which was on the muffin slide. And then the second or the third type we can look at it is going to be in terms of a graph, and that's what this example is. So let's take a look at this example and how we can graph it and see the function relationship. Here it says, let n be an integer where n is greater than or equal to 2. And they already have it defined here in our ordered pair, or it's part of the ordered pair, so we have to be at 2 and higher. Graph a function that shows how many elements of an ordered set of n different integers. So we have to have 2 different integers for this set, 3 different integers for this, and 4 different integers for that, are greater than the median of that set. So what I'm going to do for you is we'll call it n and m for our median. How many are in the median of it? So this is going to be kind of our ordered pair. This is kind of like our x and our y. Now this is just a little tricky in that what they're saying. They want us to write a set of n different integers. Okay, fine. And n has to be greater than or equal to 2. So a set of 2, I'm going to pick n different integers. Let's just pick 3 and 4. Now they want us to say how many elements in that set the integers are greater than the median of that set. Remember, median is the middle number. So the middle number between the set 3 and 4, there is no exact middle number, so what you do in that case is you add those 2 up, and then you divide by 2, so it's 3.5. So the median for that first set is 3.5. How many elements in that set are greater than 3.5? It's going to be 1, which is the number 4. Now, for the second time, they want us to have a set of 3 elements. They have to be different integers. I'm just going to pick, let's do 2, 6, and 10. And they want to know the median of this set, and then how many elements in this set are greater than the median. Well, the median is the middle number, which is 6, and there's only one number greater than that. Let's go to 4 elements. Let's just pick 5, 10, 12, and 20. Median of this set would be the average of these 2 numbers. Average of those 2 numbers would be 11. Therefore, 2 elements are bigger than 11 in that set. And let's look at one for 5 elements. Let's just pick 2, 4, 6, 8, and 10. The median here is 6, and the number of elements greater than the median is 2. Now, if we continue this on, there is going to be a distinct pattern when there's 6 and 7 elements, when there's 8 and 9 elements. For 6 and 7, there's going to be 3 and 3, 8 and 9 is 4 and 4. And if we graph this relation, what we're going to see, 2, 1 is right there, 3, 1, then we go to 4, 2, 5, 2, 6, 3, 7, 3, 8, 4, 9, 4, and that. This is a graph of a relation, and we actually can tell that this is going to be being a function when we talk about the vertical line test. Now here in this next example, we actually have an exponential function already graphed for us. This is the equation of the function. They want us to state the domain and the range of this while it's in an equation format. Fine, the domain are what the x's can be, the range is what the y's can be. Okay. Now in this case, the domains, if we look at the various ordered pairs, here's an ordered pair right here. It looks like roughly the ordered pair 3, 4. Okay. Here's another ordered pair, it looks like 0, -3. Okay, and I might be able to find some other ordered pairs. Now, what they don't want you to do in this case is say, oh, the domain can be the number 0 and 3 and 4 and 5, because this function continues on forever. Look at this right here. There's an arrow, and here there's an arrow, which means it goes on forever. The domain of this function, you want to think about this. What can x be? Well, can I choose 1 for x and land on the graph? Sure, I land there. 2, I land here. 3, I land here. 4, I land here. -4, I land here. Is there ever a number that I choose for x here that will not give me an answer? Look at the graph. If you graph it and this graph doesn't have any breaks in it left and right, the answer is the domain x is all real numbers. And that can be my final answer. Okay? Or another shorthand you could do, x is the element of all reals. Or you could just write out in an equation format or a sentence, x is all real numbers. That's fine. Now the range. The range is the y's. The range is the output. It's right there. Well, what axis? The y-axis is right here. It goes up and down. So when you're looking at a graph, when you're determining the range, you're determining the height of this graph. Okay, when you did the domain, by the way, the domain is all the inputs or the x's. You just visually look at it left to right. If I read this graph left to right, if I go this way, I'm going to notice it continues on and on forever. The range is unlimited. That's why I said it's all reals. Or I'm sorry, the domain is unlimited. But look at the range. The range is the output or the y values. It's the height of this graph. The height of this graph, we have an issue. It doesn't start until about right here. This thing has what we call an asymptote. So the asymptote for this graph, this function starts, it looks like roughly at -4. But it's not quite at -4. So what we write is the range is all the y's greater than -4, but it does not include it, so do not have the =2 sign there. Again, I already mentioned this. A test if an equation is a function is the vertical line test. Let's just save you some time here. We have two graphs, two equations. Get your graphing calculator out. Put this in your graphing calculator. I'm going to give you a quick sketch. This guy right here is going to look something like this, roughly. Okay? This guy over here is going to look, let me fix this a little bit. Something like that. Okay, the domain and range of this function. If we look at this parabola, y equals x squared minus 4, I want you to pause the video and figure out how would you write the domain and range, and then do the same for the second graph. So pause the video, write the domain and range, and see if your answers are correct. All right, here's what you should have gotten. Remember, for the domain, what you want to do, since this is the x-axis, you visually just look at the graph left to right, which is how it looks. This graph, yes, it doesn't have anything over here in this space or over here in this space, but it does have answers for x at these values. I could put 10 in there and graph somewhere up here. It would be way up here. So the domain for this function is all reals. I can put anything in for x and get an answer. My calculator is not going to say, wait a second, if you put 30 in for x, 30 squared minus 4 is going to say no answer, I can't calculate it. Of course it can do 30 squared minus 4. Okay, so the domain is all reals. The range, this thing actually has its vertex at the number -4, so it does include it. So be very careful. The range is the height. It's the y-axis. So look at the graph up and down. Well, this thing doesn't start until -4 and everything higher than -4. So that's why the range, which is the output or the dependent variable, is y is greater than or equal to -4. Now the second graph over here is our exponential function. This one here, what can you put in for x? Can I put a -1, a -2, a decimal, a fraction? Absolutely. The range for this function is all real numbers. I just wrote it differently. I put x as the element of r. That's fine. Or just write x as all real numbers, like in one long sentence. That's fine. Now the range of this function, you have to be careful. My graph is a little off. So if you graphed yours, you're going to notice it's a little bit down further and then it comes up. The height of this graph is the range. You're going to notice this graph doesn't start until a little bit after 0. So it's all the y's greater than 0. Okay? Exponential functions have asymptotes. These are vertical or horizontal lines they get close to but never quite cross. Be careful, this thing has an asymptote on the axis. It gets close to 0 but never quite gets there. Now we're almost done. This slide is a pretty easy one. This notation right here, just know how to say it. It is said as f of x is how you say it. Okay. Here's the question. Suppose f is the function defined by this rule right here. They call it a rule. You guys, it's an equation. It's in function format. It's the same thing. And they're saying for all real numbers x. So they can put any type of real number in an x and get an answer. They want you to evaluate f of 5. Fine. That's easy enough to do. It's not hard. Know how to do this without your calculator though, you guys. What you would do is put 5 in for x. So I go over here where the x's are and say f of 5 is equal to 4 times 1/2 to the 5th power. Okay, be careful, you guys. What this means in exponential format is the rule you learned last year is you can distribute that. And do PEMDAS. Always do parentheses, then exponents, and then multiply. So do not multiply this thing by 4 until the very last end. PEMDAS. Okay? Parentheses and exponents. That's our first, and then we'll come back and multiply. So this is going to be 4 times 1 to the 5th power over 2 to the 5th power. 1 to the 5th power means do 1 5 times. So 1 times 1 times 1 times 1 times 1 is 1. So that's 4 equal times 1 over 2 to the 5th power. That's 2, not 10. It's 2 5 times. That's 32. Multiply straight across. The answer here is 4 over 32. We would always simplify that fraction. The answer to this is the fraction 1/8. And I'm going to tell you, on a test, you need to be able to do this without a calculator. Your calculator, the test will not allow you to use a calculator for this. You need to keep it in fraction format and show me how to do this. This is basic math from Algebra and Algebra 2. Okay, Part B is an interesting question. They want you to determine, is f of -2 plus 3 the same as f of -2 plus f of -3? Basically, can we distribute function notation? Is the big question. I want you to pause the video and just think about this for a second or two, and then when you're done pausing it, I'm going to pop the answer up, and you're going to see if they are equal or if they're different. So go ahead, pause it, and think about this for a second. Here's what we have. When you do the math, what you need to do on this side is realize that you do parentheses first. So they actually want you to find f of 1. F of 1 is the answer 2. Okay. The right-hand side, you need to find f of -2, and you need to find f of 3. F of 3 is pretty straightforward. It's right here. That actually, f of 3 is going to simplify down to 4 over 8 or 1/2. Okay. Now be cautious on f of -2. This is a good review. If I put -2 in here, I can now distribute it through, which I get this side here. Now a negative exponent, to get rid of it, you just flip-flop it across the fraction bar, and I have this. 2 squared is 4. 4 times 4 is 16. So it's 16 and 1/2. What this shows us, by the way, folks, is function notation is not distributive. We clearly get 2 different answers, so be very careful. So last slide, and what they want you to do here with the same function is evaluate f of q plus 1. Fine. This used to be f of x, by the way, folks. So notice they replaced x with q plus 1. So you go in wherever x is, and you replace it with q plus 1. It's as simple as that. So f of q plus 1 is equal to 4 times 1/2 q plus 1. Now, we're going to get into more details on how you can pull this apart. For now, I'm just going to have us keep the function in this notation, and that's all you're going to have to do. If you do recall, though, this property of exponents is going to tell me that I can rewrite this, by the way, as 4 times 1/2 to the q power times 1/2 to the 1 power, and then I can combine the 4 and the 1/2 and get 2. So this simplifies to 2 times 1/2 to the q power is what they want you to take away from that. Again, I'm okay right now because we will get into this breaking down later in the year. If you're successful on the entrance card, this is going to be your modified assignment. Everyone else, this is it. And just do pay attention in class to see if I justify any of the problems. Good luck on the homework.